Hello, everybody. Last two videos, we've seen that there are problems that are very hard. There are problems that are not even recognizable. First, we saw it using a counting argument. And in the last video, we saw that there is a specific problem that we care about, not ATM, that is not recognizable, and ATM, which is not decidable. So that's kind of sad news, but is it the only problem? I mean, if it's just a coincidence and there is just one problem that we cannot decide, perhaps it's not so bad. Well, it turns out that there are many, many problems that are not decidable and not recognizable. And now the question is, how can we prove these problems? And one approach is for each one of them to try to find a clever argument like diagonalization that would show that if you decide these problems, something strange happens. But that would be just too hard. And instead, what we're going to do is use reductions, or more specifically, what we call mapping reductions, to show the connection between many other problems to ATM that would imply that these other problems are also not decidable or not recognizable, depending on the problem. So reductions are kind of maybe one of the major techniques, if not the major techniques we're seeing in this class. And we're seeing it in a way which is opposite to the algorithmic manner of using reductions to solve something. Here we're using reductions to show that something is impossible. And this is something we'll meet again when we'll talk about complexity. We'll see reduction to show that something cannot be done efficiently. So our concrete problem was ATM. We showed that ATM is not recognizable. So it's recognizable, but not decidable. And as a corollary, we showed that not ATM is not recognizable. Let's look at a second problem, the halting problem. The halting problem also is a language over pairs, M, which is a Turing machine, and W, which is a string. And these are pairs where M is a Turing machine that halts on string W. So in ATM, we wanted M to halt and accept W. In halting, we only care that M halts on W. This is definitely something we want to know. I mean, we would love not to run algorithms that run into a loop. So if before running the algorithm, we can check that it's going to stop, this would be a positive thing. And the theorem is that halt TM is undecidable. So let's see a proof. Assume for the sake of contradiction that there is a Turing machine H that decides alt TM. And we're going to use H to construct a Turing machine M prime that decides ATM. This, of course, is going to be a contradiction because there is no Turing machine M prime that decides ATM. So let's see how we're going to define M prime. So M prime is a machine that is supposed to decide ATM. The way it will do it, it will first run H on MW. H is the machine that tells me if M halts on W. If H rejects, it means that M is not going to halt on W, and definitely it's not going to accept, so M prime can also reject. If H accepts, then we can safely run M on W because it's going to halt, and when it halts, we can do we can output what M does. If M accepts, we're going to accept. If M rejects, we're going to reject. But this simulation is going to surely stop, surely going to halt because MW is in halting. So pictorially what we have this machine this machine H that decides halting. It gets an input MW and it's going to tell us if M halts on W. We're going to take this machine and use it as a subroutine within a bigger machine that is going to decide for us ATM. So the input for ATM is MW. We're going to feed it first to our subroutine H and C. If M doesn't halt, then we can reject, because we know that M definitely doesn't accept. If it doesn't halt, it doesn't accept. And if M halts, then we can feed it to M itself. So we feed W to M, and we output whatever there is to output. So this is kind of, we can actually, there is a proof of that halting is undecidable just by a diagonalization argument, pretty similar to the one we saw for ATM. But instead of having two of these arguments, here we did it directly. And we can often do something like this. We can often prove that a language L is undecidable by showing that if L is decidable, then so is ATM. Meaning we show a reduction from ATM to L. We reduce ATM to the language L, and we'll call this ATM is smaller equal ML. Or in words, ATM is mapping reducible to L. What we saw actually is not a mapping reduction. We'll talk exactly what a mapping reduction is. So what is a mapping reduction? A mapping reduction is a function, and it is a computable function. So let's discuss what is a computable function. So a function f that takes a string and outputs a string is computable if there is a Turing machine M that always stops when it has the input. For any input, it always halts, and for input W, it's going to halt when f of W is written on the tape. So when we wanted to have machines that compute a language, the machine has to just halt and either accept or reject. Now we want the machine to halt and write the output, which is f of W. That shouldn't surprise us. Any programming that you've done usually didn't just check if something happens or not, but add some output to it. And now that we have what a computable function is, we can say that a language A is mapping reducible to a language B, which will write A smaller equal M B, if there is a computable function F such that for every W, W is in A, if and only if F of W is in B. So what does it mean? Why is it a reduction? It's a reduction because instead of trying to answer if W is in A, we can compute F of W and then answer if F of W is in B. And this if and only if W is in A, if and only if F of W is in B, means that solving the problem W in A is exactly the same as solving the problem F of W is in B. So we reduced one problem to the other. We reduced the problem in A to the problem in B, and that's why we say that A is reducible to B. F is called mapping reduction or many-to-one reduction from A to B. It can be many-to-one because nobody says that two different W's cannot map to the same problem. In fact, in some proofs that you'll write, you will have the same, you'll have many inputs go to the same output. Pictorially, what we have here is a reduction, is a function that goes from strings to strings, and the function f, which is computable. You can actually follow these arrows, these yellow arrows, and such that such that you have that if you are in A, if you start in A, you end up in B. And if you start outside of A, you end up outside of B. So the question of whether this point that you reach is in B or not in B is exactly the same as the question of whether the original point is in A or not in A. And so we say A is mapping reducible to B and write A smaller or equal M to B. And I want you to remember that notation by thinking that A is somehow weaker than B. And we'll see exactly why, but that's the way I remember how to write it. So A reduces to B, it means that it is kind of weaker from B, or not stronger than B. One nice property that we have is transitivity. If A is mapping reducible to B and B is mapping reducible to C, then A is mapping reducible to C. And to see that, we just need to compose the two reduction, to compose F and G. Because to this function that takes you from that first applies F and then applies G, will first be computable because F and G are computable, and then it will have the property that when if you start in A, you'll end up in C, and if you start outside of A, you'll end up outside of C. And now we see how we're going to use it, and as I said, we're going to use it in the computability or complexity theoretic way of using reductions, kind of in a negative sense. But first, let's see the algorithmic sense. So if A is mapping reducible to B and B is decidable, then A is decidable because you can reduce your problem to B. To solve A, you can reduce it to B and solve it there. So kind of with more details, M decides B, and let F be a mapping reduction from A to B. To decide A, you can build a machine M prime that first compute F of W and run M on F of W and output its answer. So F of W reduces the problem to B, and in B we know how to solve it using M. So W is in A if and only if F of W is in B, meaning that W is in A, meaning that implies that F of W is in B, and therefore M prime accepts W. W is not in A, means that F of W is not in B, means that M prime is going to reject W. Similarly, if A is mapping reducible to B and B is recognizable, then A is recognizable, and the proof is the same proof. M recognizes B, F is the mapping reduction from A to B. To recognize A, we build a machine M prime, just as before. You compute F of W, you run M on F of W and output its answers. If you get it, so the reason you don't get something that decides is because M doesn't necessarily decide. M can run forever. In that case, M prime would run forever. But whenever M is going to halt, it's going to give you the right answer. So these are the two positive ways. If you have a reduction, you can deduce the decidability of A or the recognizability of A from those of B. The counter-positive is, the corollaries are that if A is mapping reducible to B and A is undecidable, then B is undecidable. Because if B was decidable, then A would be decidable. And similarly, if A is unrecognizable, then B is unrecognizable. So in this sense, B kind of gives us or A gives us a lower bound on the difficulty of B. And B gives an upper bound on the difficulty of A. So if B is decidable or recognizable, we can deduce it for A, and if A is not decidable or not recognizable, we can deduce it to B. Let's go back to the proof that halting is not reducible, and we didn't present it this way, but we can show how it can imply a mapping reduction from ATM to HALTM. So we can reconstruct this proof and show that and show a mapping reduction from ATM to HALTM that would show that HALTM is not decidable. So for that, let me go to the board. So we want to show again that HALTM is not decidable, and we will show it by showing a theorem that ATM is mapping reducible to HALTM, and I'm doing it, and I'll do it a few of those, and I'll try to do it slowly, so so you kind of see how to mechanically do it. So what does it mean? It means that if you're writing it this way, we want a reduction in this direction from ATM to HALTM. And the first thing we need to do is syntactically, what does it mean? So we want a function from these inputs to these outputs. We need to ask ourselves, what are the inputs? How do the inputs for ATM look like? So the input for ATM look like MW. And an input for HALTM is again a machine and input, M prime and W prime. And now we want to ask ourselves what does this proof needs to do. So we need to have that MW is in ATM if and only if M prime W prime, so it is in ATM if and only if M prime W prime is in HALT. So let's continue parsing it. What does it mean that MW is in ATM? It means that M on W accepts, and what does it mean that M prime W prime is in HALT? It means that M prime on W prime halts. And now let's construct this M prime and W prime. So the way we'll construct it, we'll first to say that W prime equals W. And we're going to create this M prime, not very different than we had before. So M prime, which inside we have M. And the way M prime operates, it gets an input X. We need to say what to do. We're going to plug X into M. And now, if it is accepting, so it can either accept or reject. If it is accept, we're going to accept. If it rejects, we're not going to reject, we're going to loop. So we're just going to implement some other machine that never halts. For example, a machine that just counts from 1 to infinity. So just promotes a counter. And of course, M can also not halt, but in this case, M prime doesn't halt. So now I want to claim that this construction works, meaning that I want to say that we have this relation. MW is in ATM if and only if M prime W prime is in alt, and W prime is W, so let's write it like this. So let's ask, if MW is in ATM, means that M of W accepts. So if I plug here W, M accepts, and M prime accepts. M prime accepts, in particular, it halts. So if M accepts, M prime halts. If M reject, then M prime is not going to halt. And if M doesn't halt, which again, it means that it doesn't accept, then M prime doesn't halt. So with this, we completed the proof. So we have that MW is in ATM if and only if M prime W is in halt, and that's a construction we wanted. So we have that ATM is mapping reducible to Haltm. And as a corollary, we will have that not ATM is mapping reducible to not Haltm. So why is this true? Try to think about it for a minute. Well, it is true because any mapping reduction from A to B is also a mapping reduction from not A to not B. You can try to convince yourself. The same mapping reduction from ATM to Haltm is also a mapping reduction from not ATM to not Haltm. The corollary is that not Haltm is unrecognizable. Of course, we could have also deduced it just from the fact that Haltm is not decidable, but recognizable. But the reduction gives us a different way of showing it. Not Haltm was recognizable, then not ATM would also be recognizable. And now I want to show the other direction. We want to show that Haltm is mapping reducible to ATM. So here we will also have kind of a reduction from inputs to Haltm to inputs to ATM. And again, we will keep the same W, so we will just revise M. So we're going to transform MW to M prime W. This is the computable function we're going to compute, to define. And the property is that M prime W accepts if MW halts, and else it loops forever. So think for a second, how can you define M prime in such a way? And if that's the case, if we can show such a reduction, then we'll have that MW is in Haltm, if and only if M prime W is in ATM, and we get the construction we wanted. So how would we, I'll give a hint about how to construct this M prime. So M prime needs to accept if M of W halts and else run forever. This is even easier than before. M prime would simulate M on W or on the same input. If the machine halts, it is going to accept. So instead of, we're going to ignore what M does. The moment it halts and want to output either accept or reject, we'll move to an accept state. And otherwise, it's not going to halt. And therefore, our simulation is not going to halt either, meaning that M prime is not even going to accept. So essentially what we've seen is a reduction from Haltm to ATM and vice versa. So they are mapping reducible equivalent, these two problems. So if kind of we we can imagine a Turing machine, and this Marlin tells the Turing machine, you know, I can give you some magical power that other Turing machines don't have. The power either to compute the halting problem or to compute the acceptance problem. Which do you want? Then the Turing machine has no reason to prefer one over the other, because you can reduce one to the other. They're equivalent to each other. We're going to see a few more examples. And again, to be able to do it more slowly, I'm going to go to the board again. The next problem we're going to analyze is the emptiness problem. And we'll see several variants of it. So empty DFA is M, such that M is a DFA, and the language that the M recognizes is empty. So M is a DFA and L of M is empty. And the theorem is that empty DFA, so what is it? Is it decidable or not? Yes, it is decidable. And why? So empty DFA is decidable because we can look at the DFA and analyze if there is any accepting state which is reachable. If no accepting state is reachable, then we cannot accept anything. But once there is a reachable accepting state, then the DFA accepts something in the language. It accepts exactly what allows you to walk on the path from the start to an accepting state. How do you verify that there is that the state is reachable? This is CS161 for you. So there are simple algorithms for connectivity. And breadth first search, depth first search. You apply any of those and you find if there is any accepting state that is reachable from the start state. So how about empty NFA? Empty NFA is the same, but M now is a non-deterministic finite automata. Still, L of M is empty. So empty NFA, not surprisingly, is also decidable. You can either directly do the same thing, so look for an accept state which is reachable, or reduce the NFA to a DFA and solve it, solve empty DFA. How about empty regular expression? So here it's the language of R such that R is a regular expression, and the language that it identifies is empty. So is this decidable? Well, yes, this is decidable, not surprisingly. For example, because you can turn a regular expression into an NFA and then a DFA and solve it there. And getting to our main course, empty Turing machine is as you can expect, M such that M is a Turing machine and L of M is empty. Meaning that this program rejects every input, or actually doesn't accept any input. So we're asking, is this Turing machine, is this a Turing machine that doesn't accept any input? And the theorem is, so is it is it decidable? Is it recognizable? Well, it turns out that empty TM is not even recognizable. And now we'll prove that. So kind of intuitively, or what would we try to do if we wanted to recognize it? We would try to run it on all inputs and see if it doesn't halt on any of them. But how can we know that you don't halt? You need to simulate and not to halt. And so kind of intuitively, you'll never be convinced that it doesn't accept anything. Perhaps you just didn't run long enough. But formally, what we'll show, so the proof, is to show that not ATM is mapping reducible to empty Turing machine. And since not ATM is not recognizable, then it will tell us that empty TM is not recognizable. So now we want a function f from inputs of not ATM to inputs of empty. So let's think, what are the inputs of ATM or not ATM? These are pairs MW. And what is the input of empty? This is just one machine. So given M and W, we need to transform them to M prime. And what is the property? The property that MW is in not ATM if and only if M prime is in empty TM. And I do it very slowly, so you see kind of almost mechanically how to do it. At the end, there is always something that requires some thought, but quite a bit of it is mechanical. You just try to see, okay, what kind of inputs, what are the properties? So let's parse that. What does it mean that not ATM, that MW is not in ATM? It means that M doesn't accept W if and only if. What does it mean that M prime is in empty? M prime doesn't accept any input X. Okay, so that's where, so that's as far as we can go automatically. We now know exactly what do we need to transform to what. We need to transform MW to M prime, and this is the property that we need. So let's think how we're going to do it. We know that M prime should accept something as long as M accept W. So the only input we care about, in fact, is W. The way we're going to do it is M prime on X checks if X equals W. It just simulates M on X and does the same thing as M would do. And if X is not W, then you just reject. So you reject outright. So if M doesn't accept W, then N prime would not accept anything, because the only X that it can accept is W. And therefore, we can conclude the reduction. Okay, so that's another example. Let's go over to yet another example, which is the regularity problem. And I'm doing it pretty slowly because if there's one technique I want you to internalize is these reductions, and actually it will become even more important and interesting when we talk about efficiency or complexity. So this is the regularity problem. Regular Tm are all the m's such that M is a Turing machine and L of M is regular. So in other words, all the Turing machines such that there is a DFA that would recognize the same problem. So it's equivalent, all the Turing machines that are equivalent to some DFA. So what do you think? Is it decidable? Is it recognizable? Well, yet again, we get that so the theorem is that regular Tm is not even recognizable. And by now we have lots of problems to reduce to regular Tm. We could reduce, for example, empty to regular Tm, but the way we'll do it is reduce not ATM. So we will show that not ATM is Turing reducible to regular Tm. This is not a bad place to pause and to try to think about the reduction yourself, following the what we did before. But now that you're back, let's do it ourselves. So what is the input for not ATM? This is again MW. And we need to transform it to the input of regular, which is again just one machine, M prime. And what we need is that MW is not ATM if and only if M prime is in regular Tm, meaning that if M doesn't accept W, we need that this will be the case if and only if the language that M prime accept is regular. Okay, so that's the reduction we need to do. And how are we going to do it? We're going to define M prime. It's a little bit similar, but slightly more complicated than the previous reduction. So M prime on X is going to do the following. If X equals 0 to the n, 1 to the n for some n, then simulate m of w, and other else you reject. So what are the two options that can happen? If m prime is going to, if m accepts w, then m prime is going to accept every string 0 to the n, 1 to the n. Because for every such string, when x is 0 to the n, 1 to the n, we're just going to simulate m on w, it's going to accept, and therefore we're going to accept it. Otherwise, we have, we're accepting nothing. And recall that the empty language is regular, whereas the language that contains 0 to the n, 1 to the n is not regular. So kind of writing it a little bit more slowly. If m, w is in ATM, it implies that m prime, so L of m prime is 1 to the n, so 0 to the n, 1 to the n, where n is some natural number, which is not regular. So alternatively, when w is not in not ATM, then we have something that's regular. On the other end, when w is in not ATM, then L of m prime is empty, is the empty language which is regular. And this concludes this reduction. We'll give one last example here, which is the equivalence problem. And this problem will actually be interesting later on. So equivalence Tm now gives you two machines M. It's over pairs M, N, such that M and N are Turing machines, which accept the same language. So these are equivalent Turing machines. L of M equals L of N. So if we ask the same questions about DFAs, then actually we know how to compute the equivalence of two DFAs. We can do it by first reducing both of them to the minimal DFA, and then verifying that the DFAs are equivalent to each other, which we have all these tools from the previous chapter. But what do you think about this problem? Is it decidable? Is it recognizable? So the theorem is that the equivalence problem for Turing machines is unrecognizable. And how do we do that? Again, by now we have quite a few examples. So we need to choose the one that we're the most happy with. And we'll show that empty Turing machines is mapping reducible to equivalent Turing machine. So again, what we're trying to do here is reduce. So we need some function that takes inputs of empty to inputs of EQ. And I'm going to tell you what this reduction is going to look like. The input of empty is some Turing machine. And it's going to get us to input for equality is two Turing machines, right? It is M, and we're going to, so to have M naught. So this is a reduction where we are actually going to keep one of the ingredients. So M is reduced to M, comma M naught, right? The input of equivalence is the same, it's a pair of Turing machines. And this reduction is going to be pretty simple. M naught is some, so is a dummy Turing machine that rejects everything. So we just have no accept states, or the accept state is disconnected from the start state. There is no path from accept to start. So we can have something like this. This is a start state, this is an accept state, and you have all the edges are self-loop here and here. So you're just going to start and end in the start state, which is a reject state. And I wanted to claim that this is a reduction that's sufficient because M is in empty Turing machine, if and only if, just the definition of empty Turing machine, L of M is equal to the empty language, which is just L of M naught. And this is just by definition, if and only if M naught are in equivalent Turing machine. So that's the last reduction I'm going to, I wanted to do on the board. And with this, we'll go back to the slides. So far we've seen a few reductions, mapping reductions that help us show that problems are not recognizable or not decidable. And the ingredients are always to first show a mapping, to argue that the mapping is efficiently computable. We didn't invest too much time in it, but this is one ingredient you need to argue all the time. And then to show an if and only if, that the input to the reduction is in the first language, if and only if it is in the output is in the other language. This is something that's often where people, so the thing that you often will forget is either to show that something is computable, that the mapping is actually computable, or you'll only show the if and not the only if, or vice versa, because you design it to do one side, but you forget to argue about the other side. All of the problems that we discussed were about computation, and I want to give you a sense that not all problems look like or directly apply to computations. So here is another problem, the post correspondence problem. And in this problem, the input is a bunch or collection of domino types, like we see here. And you want to compose them in some order, and you can reuse domino types as many times as you want, such that the string on the top will equal the string on the bottom. So here, if we take the first two, and then we'll have on the top BAA and on the bottom AAB, and this is, of course, not a match. But if we first use this one and then use the first one, then we will have ABA on the top and ABA on the bottom. This is, of course, a very short sequence. And in general, the sequence can be large, and you cannot, and you can reuse dominoes, so there is no way to just exhaustively check all combinations. So this is the problem. P is in PCP. This is, by the way, not the most interesting PCP, I think, that we will encounter in this course, such that P is a set of dominoes with a match. And it turns out that PCP is undecidable. And the proof, I'm not going to talk about the proof. The proof is in CIPSR. I think it's a reduction, perhaps from ATM. And what this shows is that although the problem doesn't look like it's about computation, the fact that you can reduce a problem about computation to PCP, it means that somehow in it there is, or it is equivalent to a problem about computation. So it's kind of in it, there is some kind of a computation going on. So to conclude, we've seen a way to use reductions to impossibilities, and we're going to see more in this chapter and even more when we'll talk about efficiency. And analyzing programs is really hard. So we've seen various things that we really want to say about programs, if two programs are equivalent, if a program halts, but we cannot. In the next video, we're going to see a way to deduce that many things about computations are not decidable or not recognizable. This will be Rice's theorem. And then we will talk about a more general notion or stronger notion of reductions called Turing reductions and what it implies. Thank you.